cannot be helped under the you know what?
So I think we can connect with this, so there should be a video.
I already connected here. So
In this case, and we need to type the project.
Oh, you're a DSL?
Yeah.
Oh.
Very soon.
does it work now?
The input. Yeah, it was. So it's.
And does anyone know how to turn on the projector?
Can I try?
Sure, yeah.
Can you turn on the display?
Oh, yeah. Display.
Not sure. Is it? Did it?
It doesn't show anything.
So there is more like a second screen.
Oh,
Yes.
okay.
Do you want to?
And maybe I should try laptop too.
Yeah. Oh. Now it shows the second screen.
Okay, let me. Okay, good. Thanks a lot, Shannon. Do you hear me well? Oh, I didn't turn on this bit. Okay. Does it work at all here? Okay, it's fine, right? Okay. Good. Okay. So welcome everyone to this class, Advanced Graph Algorithm. And yeah, so let me start with just some logistics. All right. My name is Tachapol Saranurak. You can call me Tachapol. And there will be, so the class is, when and where. I just put it here. And if there is some time that for some reason we need to take class online, we will do it in this link. Also, for the office hour, I will be around in this Gather Town. Have you tried Gather Town before? It's like the virtual. Yes. Okay, cool. Yeah, it's like a virtual space, and you can hang around. I think it's quite cool, and yeah. So, but if you want to meet in person, we can meet too. But just by default, I will be in Gather Town, and PSR link and lecture recording will be in this link, and yeah. So the grading of this class will be based on problem sets, and there will be scribe note too, and also research project. That will be quite important in this course. You will either write some survey or solve open problems, and I will talk more about this maybe like on Friday. And there will be some like final exam too. Yeah. So just kind of normal setting, I guess. So any question regarding logistics? Okay.
So the discussion session, is it compulsory or is it a recitation kind of thing?
I would try not to make it compulsory, but sometimes I will try to actually discuss open problem there. So I would like to suggest to come. Yeah, but at least maybe like not like all the material will be in lectures, basically the main material of a class. Yeah. And so about the theme of this course, basically the central object in this class, it will be something called expander. This is like a very important object in TCS. By TCS, I mean theoretical computer science and math. There are so many applications and so important. So in this course, we will see basically one aspect why this object is so powerful, why expanders are useful for designing fast graph algorithm. And but there are many other areas that expanders are like useful. For example, coding theory and pseudo-randomness and PCP. Something about like how to check the proof fast. And so basically today we will already discuss what is expanders. But before I tell you what it is, so I want to tell you first what it is morally, or like what we want it to be, what it should be. So when you look at the definition in math, usually you should try to ask for this actually. Most important definition in math, there are like some motivation behind it. So sometimes formal definition is not too useful to know. Like we should know like why we want that. And so expander is something which is like, basically it's like a sparse complete graph. And by complete graph, I mean, so it's just a graph where like you have edges between every node, right? It's a clique basically. So a complete graph is very dense. It's just maximally dense. And expander is a complete graph which is sparse. So this seems a bit contradictory. But what I really mean is that it is a graph that behaves like complete graph, but can still be very sparse. It inherits all the good thing about complete graph, but and still very efficient in the sense that it can be very sparse. So basically, it will have these following properties. There are like 4 perspectives of them. Each of them is quite important. So first, this graph is sparse graph, but it's still kind of well connected in the sense that it is robust against deletion. Doesn't matter that much what it means right now, but also it had like another perspective is that it allows all-to-all routing, and there are other perspectives about random walks and some other perspective about in the algebraic perspective. So each of these is I will basically try to explain what it means. Like it looks completely they look completely different, but it turns out that they are all equivalent. So this is the nice thing, nice phenomena that like when there are some object in math that you can describe it from completely different angle, it means that there are something fundamental about it, right? And in some basic algorithm class, you might have seen maybe like a min cut and max flow, kind of totally different thing, but they are dual to each other. Expander will have some of that flavor too, but actually there are 4 ways to look at it. So this is quite cool. And yeah, so first half of the course, I will try to explain this equivalence. And along the way, we will see a lot of nice mathematical concepts like flow cut gap, metric embedding, and some other buzzword that is nice. And just, maybe I should have a pointer. Yeah. And along the way, we will see a lot of algorithmic application just by knowing these equivalence views. You will get some nice algorithm from it. So that's the first half of the class. And for the second half, once we have like a kind of comprehensive understanding of expander, we will try to develop very fast algorithm from it, like good algorithm based on expander. So this is quite fruitful. Surprisingly, I don't know why, but like, I guess because expander is really powerful. It turns out I can like, in the past 5 years, I already like can manage to get like almost maybe 20 papers just from trying to understand this and look into classical old problem in computer science, and then apply these tools, and it turns out that can break like a many decades barrier that people cannot improve. So this is like powerful, and I hope that I can explain these ideas, and maybe you can apply these two to other things by yourself. So, and by good algorithm here, there are many definitions of good algorithm actually, but I want to clarify a bit what kind of good algorithm we want to develop based on extenders. So maybe like there are many criteria of good algorithm. Can you maybe describe what do we want to say when algorithm is good? What is the criteria, please?
So one is we want our algorithm to be efficient.
Yeah.
We want it to be like the correct answer.
Right. Good. So fast and correct. Yeah. Very good. What else?
Less space.
Yeah. It shouldn't be just fast like a small time. And it should have like a small space too. Yeah. What else? Yes. Robust?
Yeah.
Yeah. In what sense?
Changes.
Sorry?
For changes.
Yeah, very good. So maybe just to elaborate, maybe like you have computed something already. Let's say you have, no problem. You have computed, let's say, shortest path in the graph, and maybe just one edge in the graph change. Do you need to compute everything from scratch? That is, if you don't need to compute everything from scratch, maybe it means to be robust against some change. And that is a very good thing that we should hope for. So to be like a dynamic. Okay. Anything else? Very good. I like that a lot. Yeah. So it should be simple. And by simple, actually, this is like one of the most important. There are two things for simplicity, actually. One is it should be simple enough to implement. Like simple to implement. But that is like if you have some algorithm in theory that is so good, but it's not implementable, then that is not going to be impactful. However, there is another thing also that is, at least it should be simple to understand. Like at least people in theory should understand it. Because if even people in theory don't understand it, then it might not be even like improved further. All right. Okay. There should be more. Is what else? Yes. Good. Deterministic. So some of the algorithm that I'm not sure how many people here have seen algorithm which is not deterministic. It's randomized. Okay. Maybe can you give me some example of those algorithms? Maybe you. Anyone? Yeah. Yeah, please. Sure.
It's
Quick sort. Very good. Yeah. Quick sort. It's very fast, simple, but it's Kagger mean cut. Okay.
It's not determinate, so you have to run a few times.
Right. Right. Yeah. Yeah. Kagger's mean cut algorithm. That is very simple, nice. But it is randomized. It might make an error too. Yeah. Quick sort as well. That never make error, but the running time might be in the worst case become n squared instead of n log n. Right. K-means, yeah, good. Yes, please.
I have a question. So you say deterministic. Are you talking specifically about the runtime or about like the output? Like some algorithms might have, multiple correct outputs.
So okay. So there are two ways to talk about randomized, like two kind of guarantee about randomized algorithm. You're right. The one is like it is Monte Carlo. So random mice. So one is Monte Carlo. So this one basically it means that it can make an error with some probability. Another one is Las Vegas. It's just a name that people give, but here it means that it never err, but the running time the running time actually is not guaranteed in worst case. Only like expected runtime guarantee. So quick sort is in this category, right? But there are several other things like Kagger, mean cut. Don't worry if you don't know this one specifically, but you can imagine a bunch of randomized algorithms that might make an error. Right? But what we want then is we want it to be deterministic. Like it never err, and the running time is guaranteed with certainty. Okay, yeah. So sometimes you don't have, you cannot get all of this thing. But if maybe sometimes you cannot get out of this thing when you want exact algorithm. So sometimes people just come up with an algorithm that give still good approximation to what you want, but they are fast or deterministic or whatever. So what we want is if it is not exact, then it should give good approximation. Okay. And there are something else also. For example, you want it to be parallelizable. So, for example, like if you have a big problem but you also have a big, like a lot of resource, a lot of computer, you would like the time to spend on this big problem is proportion, proportion to like the more resource you have, the faster you can solve your problem, right? That you want to. And there are something more, but like this is like actually basically almost everything that I came up with too. But actually, so you have list. It is should be correct, should be fast, deterministic, parallel, distributed. By distributed, I mean like if you have a bunch of computer, like think of internet, right? You have a bunch of computer like spreading around the world. Can you actually compute something just by letting this computer in the world like talk to each other in the distributed way and then solve it? Okay. Dynamic, low space, simple to implement, easy to understand. Is there anything else you can come up with? I would like to know too. Yes?
Powerful.
Powerful?
Like some machine learning algorithms, they are not fast, they are not simple, but they can solve a lot of like problems.
Oh, I like that actually. Yeah. So like it is robust in the sense that just one single algorithm, you can use it to solve so many things. Yeah. So like, okay, powerful, but I mean, what is a good word for this? Yeah, anyway. But so I want to just let you know that like there are many aspects of an algorithm being good, but all of like algorithm research basically we have kind of some ideal goal, which is we want to come up with an algorithm that satisfies not if possible all of this, but sometimes it's not possible to certify all of this simultaneously, but like at least we have some ideal goal. It's not just like a scattered direction, right? We have some common thing that we want. And so my hope is that for the second half of the course is that I want to basically tell you some of the good algorithm based on expanders. So one is one thing that is quite nice is I will tell you about how to compute MacFlow. In like a basic algorithm class, you might have seen algorithm for computing exact MacFlow, like Ford Fulkerson, or things based on blocking flow, right? Here we will see, okay, but those algorithms are not like also, okay, it is simple enough to be taught in basic class, but it is not so fast yet. The running time is like, if the graph is of, so let's say, the running time is not linear basically. But here we will see how to compute MacFlow, although not exact. You have some approximation guarantee, but it's super fast. It's near linear time. By near linear, I mean if the graph have m edges, then the running time is just m times polylog. So kind of scale almost linearly. Yeah. So this is like one of the very important result. That is actually like, so blocking flow and Ford Fulkerson these are developed like maybe in the 60 or 70, right? But this one actually is just shown by Jonah Sherman quite recently in this year. And since then, there are so many exciting development in algorithm. So my point is, even like basic problem like MacFlow, there are a lot of exciting things still happening until like last month, something like that. Another very basic problem is shortest path. You all learn about Dijkstra, how to compute Dijkstra, and that is very fast already, right? Dijkstra is linear time, or like almost linear time. But Dijkstra is actually not parallelizable. Okay. So what we will see is, we will see that how to compute shortest path approximately, but the work that you send is still nonlinear, but the time, the parallel time, is actually polylog. So very fast in parallel. Okay. That is a very nice algorithm too. And basically we will see other things along the way. Specifier, oblivious routing, dynamic algorithm, and so on. So yeah, any question about the theme of the class or what you would like to see actually, or you hope to see? Okay, so yeah. So in this class, actually, I will assume some background knowledge. You can always ask questions, but sometimes I might just like tell you, okay, you can look up about this topic where you can look up about that. And the thing that I will assume is like basic algorithm and data structure, like sorting, BST, graph searching, shortest path, MacFlow, those kind of things. Basic graph theory, and basic probability, union bound, expectation, and so on. Or Markov bound, Chernoff bound, right? Those kind of things. And I hope I will review this briefly, but I hope like I will talk, like just sometimes just state the linear program for some problem, and its duality. So the notion of how to derive, given a linear program, how to derive its dual, that I will sometimes I just derive it and say that this is a dual, and you need to, if you want to verify that, you need to know actually how to derive a dual. Okay, so that is.
What is oblivious routing?
Oh, not today, but it's a cool thing. You'll see, yeah. Okay, so now I will start going to the meat of the class now. All right. Any question before we start? Yes.
May I ask, are they still on the canvas already? Or?
I can do it now actually. So let me actually just put it there, if maybe that's convenient for you. Sure. Okay.
Thank you so much.
Sure. Okay. All right. So So I will start now, all right? So the first thing to know about, like the key thing in this class is expander or expansion. And first thing to know is that there are actually many variants of the definition, but they all capture the same thing, which is the notion of being well connected, the graph being well connected in some sense. And today we will see like how like definition of expander can be derived naturally when the notion of well connected means being robust against some deletion. As I said, like there will be 4 ways to look at this notion of well connected. Today we will see the first one. Yeah. So just imagine this, like suppose that you have like a graph G, okay, and like thing like this. If you have a graph G, and suppose that you delete the edges in the graph, and what you want is that you want that G should be well connected in the sense that after deleting the edges in the graph, the size of the largest component is still quite big. The size just reduced by like the edges. So like what I mean is, think like suppose you have a graph G, and let's say let D be the set of the edges that you want to delete, right? And let's say G prime is the graph after deletion. And what will happen is that maybe after you delete these edges, some part of the graph is disconnected by the deletion. Like it becomes this part. But the total number of edges of this thing that get disconnected from the graph is kind of small. It's just proportional to D. Okay. Like you need to think like if you have a graph and you actually want to cut it in half, you actually need to delete like really a lot of edges to make it really well separated. Yeah. If you delete small number of edges, you can just disconnect small part of it. That's what I mean. And for example, there are some graphs that totally not satisfy this thing. For example, if a graph is a path, right? If you just delete one edge here, then like the graph is disconnected completely, like half and half. And can you tell me like what kind of other graph that is not like this, or the graph that actually satisfy this? Any example or non-example? Yeah. If you have binary tree, like this, and so on, right? It doesn't matter. If you just cut it here, then just by one edge as well, the part that get disconnected is like as big as half of a graph. So that's that example. What else? Cycle, very good. How about a grid? Is it good or bad? A grid is A grid is like this thing. So it is at least like better than binary tree of a path. But you can see that it's not as good as we want here, because if you cut it around here, right? How many edges do you need to cut? Something like, if there are like n nodes here, then you need to cut like root n edges. But you can disconnect n guys here. So this is not proportion. Like the thing that get disconnected is not proportion. Yeah. What about star? A star. Yeah, star is actually good. So yeah, so a path or cycle is bad. And a good one is like a star or complete graph, obviously. Complete graph is just so well, like, it's just the most well-connected graph, right? What about and the one that is bad for sure is the dumbbell. By dumbbell, I mean, is a clique here. Is a two complete graph connected with just one edge. So this is bad, right? Yeah. So when we say that the extender is a well-connected graph, so at least extender should certify this thing. It should certify this property. And this actually leads to like a definition of conductance. That is a formal definition. So now let me tell you the definition that captures this notion formally, right? So let's say that you have a graph G, which is undirected and unweighted, and just some notation given to, this is G, given to a set of node A and B. Here, E between A and B is just all the edges between the two sets. Yeah. And I will use partial S. Here is just the number of edges crossing the cut. So partial S is, if you have a graph and this is S, just all edges going out from S. That is all the set of cut edges. Okay, some notation. And next notation is volume. Volume of the set. This is just, I define it to be volume of S. It's just a sum of the degree inside a set. Yeah. Okay. By the way, volume is just really what I mean by volume is essentially just the number of edges incident to the set. So volume is just almost the same thing as the number of edges incident to the set S. Like it basically counts edges inside a set or edges that go out of S. But so when you think about volume, it's just this number of edges incident to the set. But it's a bit more convenient to think about volume because, for example, volume certify this thing, right? If you have a volume of S and volume of the guy outside S, then it sums up to be the volume of all the graph. And the volume of everything in the graph is just twice the number of edges. Right? Each edge is counted twice. Okay, so now comes the definition of conductance. So definition of conductance is this. We say that the conductance of S in G, which is denoted by phi G of S. This is just a ratio between the number of edges going out of S compared with the volume of S or the volume on the smaller side, other side. So for example, if this is a graph, and if S is on the smaller side, right? If this is like less than half, then conductance is really like just comparing edges here with edges here. So everything that go out and also inside. So that's conductance. Yes?
So a quick question. So, like for example, the like how to say that,
partial. Yeah.
Yeah. So basically, when we say like we were counting, like, so for example on the top we're counting the numbers that are getting number of the edges that are getting cut, and at the bottom we're counting the volume of edges after the cut, or like including the edges that was getting cut.
Include the one that is cut. Yeah. So the volume really just kind of count the blue one and also the guy inside.
I want to ask, so are we assuming there is no isolated vertices in this graph?
Let's assume that. Let's say that the graph is connected. So you are worried that otherwise maybe the volume is 0. Yeah. So let's say that we don't need to assume that the graph is connected or like it doesn't have isolated vertices, but the conductance is really just defined when the volume is non-zero. Yeah. And so basically the cut have low conductance if you just need to cut few edges and you can disconnect a bunch of edges from the graph. Right. And the graph now, this is the definition of conductance of a cut. And we will use the same word for defining conductance of a graph. And that is defined to be just, it's just minimizing overall conductance of a cut. Okay. Yes?
So a quick question for the second one, conductance of the graph G. So, so basically S is like all the subsets of my vertices.
Yes.
Right? So are we defining any cut in this case? Or like, for example, we take a subset of my vertices and assume all the edges get connected to the main V's getting cut. Is that kind of the idea? Or like you'll give us a cut, specific cut?
So I'm not sure I understand the question actually. Or can you?
Of course, yeah. So can I say, for example, now I'm taking any subsets of my vertices as my S, and then I cut it off from the rest of the V, and then doing a calculation of that, and then I'm taking like a full.
Oh no! You really just start from V as a whole vertex set, and like think of there is no action going on actually. It's just you have set V, and for each of the set S, you don't cut anything out. You just look at this set and measure the conductance of that set and minimizing overall set. That is a conductance of the graph. Yeah. So the way to actually write it like more nicely is just just all set such that the volume is non-zero, is strictly more than 0, and not everything. Yeah.
You think the properties of a subset and not one.
There's a subset and not equal.
Yeah. Well, when I use this subset, I really mean not equal.
Oh.
Yeah. If I otherwise I will use this thing.
I heard the standard is that you do the subset and
I guess it's just some convention that doesn't matter. Yeah. Just remember in this class, here I mean subset equal, and here I mean strict subset. Okay. Okay. So just small observation about conductance. So you can see that conductance of a card is just some number between 1 and 0, right? And the conductance is 0 if actually this is actually you don't need to cut any edges. So like this part is disconnected from the graph already. So that's when it's 0. And the conductance of a graph is 0 if and only if the graph is not connected. Okay.
Does that make sense? Yeah. That's like somebody asked, like, what if it was all isolated vertices and like conductance is undefined?
This is a corner case, so let's ignore this. Yeah.
Like, as long as it's disconnected, it doesn't really matter whether that's completely separated. It's just always going to be 0, right? For example, just one edge was separated, it would still be 0.
Yeah, I think he means that like if this is a graph and this is just isolated vertex here, although this graph is not connected, but the conductance of this cut is undefined, just because there is no volume here. So maybe just think like every node have a self loop that okay. So just a bit more of terminology, right? So I will say that a cut S is phi sparse if the conductance is less than phi. And that makes sense, right? Conductance, if small, then it means that it's kind of sparse. Like you need to cut just a bit to disconnect things. So this is the definition. And G is a phi expander if the conductance of a graph is at least phi. So just from this definition, it means that a graph is a phi expander if a graph have no phi sparse cut. Okay. So and you should think like if a graph, like the larger of phi, the more well connected it is. So we can hope for like maybe a graph is actually, let's say when I said that the graph, let's say is like 0.1 expander. That means the graph is very well connected actually. But this thing can be, in the worst case, can be like 1 over n or even 0, right? When phi is like this, it means it's not well connected. Okay. So let's try to, like, this is a bunch of definitions, so let's try to familiarize it a bit by looking at a bunch of examples. So, so you can, let's see. What is the conductance of a path? How big it is? How small it is?
2 by n?
Yeah, something like order of 1 over n. Yeah. So because you just need to, the sparse cut is around here, and the conductance of this cut is around like a 1 over n. So conductance is something like 1 over n. And cycle, something similar, like 2 over n or order of 1 over n. Right? How about grid? Yeah. If it's a grid, then yeah, we have kind of saw it, right? That the sparsest cut is basically somewhere here. And this is, it gives the conductance of something like 1 over root n. And how about a star? Yeah. So a star is very good. So like no matter what, how many like edges you want to disconnect that, if you want to disconnect the guy with volume, let's say k, you need to disconnect, like you need to cut something like k edges. So the volume is, the conductance is something like 1. Complete graph, also like order of 1. Okay. So now,
I guess the conductance of a star is all it's a constant in one part.
it is. Isn't it just 1 or 1 over 2? I think so. I think it's just 1, right? Yeah.
What's complete graph not 1?
The complete graph is not exactly 1 because, let's say like you cut, if you want to cut the set S, you cut a bunch of edges here, but actually once you cut it, you get some edges actually that is actually completely inside S, right? So it's not like you need to cut all the edges incident to S, but almost everything. Okay. So now let's see that actually conductance really like capture the notion of robust against edge deletion that we just like saw from the motivation that we want to capture. Let's verify that it indeed captured this notion of well connected. Okay. So actually, maybe. So what do I want to say is this? So let's say that you have a graph G, okay, and let's say you delete some edges from a graph. Okay, you have a graph, you delete edges from a graph, and let's say that delete edges. And if the graph become like maybe something like this, and I will call that like they become like from connected they become disconnected, and there are a bunch of connected components. I say that the component is small if the volume of this component is at most half of the volume of original graph. Okay, just a small definition. And here we can actually, what we will prove is this. That is, the graph have conductance at least phi, if and only if, when you delete any set of edges D, then the total volume of the small, like if you count the volume of all small component, the total volume here will be bounded by like D over phi. Okay. And actually the proof is kind of simple but tedious. It's almost by definition. So let me actually just show you one of the direction of the proof, and you can look it up. It's really not that interesting. So let me prove one direction. All right. If suppose that the graph actually have conductance less than phi, then I will say that okay, actually I can find a set D such that once I delete from the graph, then I can disconnect more than D over phi edges from the graph. I can disconnect more than D over phi volume from the graph. So the idea of the proof is so simple. So if the graph is G here, and the fact that it has conductance less than phi, it means that there is a sparse cut, phi sparse cut. This is just from definition, right? You have a phi sparse cut S, and what edges we should delete? It's just edges crossing the cut. Okay. And let's try. I claim that this, if we define D to be like a partial S, then this is this will satisfy the claim. But this is like a by definition basically, because once we delete D from a graph, then this part will become a small component for sure, right? And how large is this part? Just from the definition, like, because S is phi sparse, so we know that this over this is less than phi, which means that the volume of S is at least this, is more than this. Right. So volume of S is more than D over phi. So yeah, it's as simple as this. And for the second direction, it's kind of similar. So I will prove that if there exists a set D such that when you delete it, then you can disconnect volume more than D over phi, then I will claim that the volume of G, conductance of G must be less than 3 phi. I have some slack here. It's not exactly phi, but 3 phi. All right. And do you want to see the proof? Or should I skip? Let's see it, right? Okay. So let's see the proof. So suppose that we have this set D that you can just delete it and you can disconnect a lot of things, right? So suppose there are two cases. Actually, you have a graph here, and let's say you delete D. And let's say that there still remains some big component after deletion. By big, I mean like, let's say that there is this guy C, such that the volume of C is still bigger than half. This is kind of the normal case. You delete small number of edges, there are still some guy which is big, right? Let's assume this. So if this is the case, then we just say that, okay, let's say that let S be just the union of all small components after deletion. So that is, after you delete D here, maybe you get a bunch of small connected components here.
So inside the D?
D is a set of edges. I mean,
I thought D was like this stuff again. Oh, sorry, no.
yeah. D is a set of edges here, but after you delete them, you get a bunch of connected components disconnected from the graph. I mean, maybe the graph G minus D looks like there is a big guy C here, and this connected component, small guys. So let's say that this is, call this S. All right. Okay. And let's verify this. So S, the volume of S will be bigger than D over phi, right? Because we assume that D is certify this. Certify that after you delete D, you disconnect a bunch of volume, which is more than D over phi. So the volume of S is at least this. And the volume of S also is less than half because C is bigger than half. And once you have this, then just look at the definition of conductance. We can see that the conductance of S is going to be, just plug in the definition here. The number of edges crossing S is D, and S is on the smaller side, so you have a volume of S here. But volume of S is more than D over phi, so this is less than phi. Okay. So this is like so we don't have a gap of like, we do get a phi here actually. We get a phi. Here we show that it means that conductance of G is actually less than phi, not just 3 phi. But there are like the corner case where actually after deleting D, there are no large component in the graph anymore. And yeah, as the proof is short, so let's just go through it. Like let's say that you have a graph and you delete D, and let's say that you delete a bunch of edges, and let's say that it become like, the graph become like this. All of the components are less than half volume less than half. Okay. And so when that happens, I claim that there must exist union of small components. So let's say that you even get like a bunch of small components like this. Yeah. I claim that you can like union the set S. You can find union of small components such that the volume of S is more than 1/3, but at most 2/3 of the total volume. Let's say that this is an exercise. Yeah. But if you can find this, like you can find S such that this is true, and then note that the number of edges that go out of S here, these edges going out of S will be a subset of D, right? Because you just need to, yeah. These edges used to be some guy in D, but you delete them. Yeah. So edges going out of S is at most is in D, but the size of D must be at most this. Why is this? This is kind of trivial because we said that the total volume of small component is this, but this thing cannot be more than the total volume anyway, right, of a graph. So D is at most phi. D is at most phi volume. Okay. So once you plug in that D is at most phi volume and the volume of S is here, then you get 3 phi. Okay, so just to conclude again, so we indeed have that conductance really capture being robust against deletion. If conductance is phi, then if you delete D edges, you can disconnect in total DO phi volume. So if phi is large, phi is constant, then deleting D edge means that you can disconnect basically D volume from a graph. Okay, so let me continue. When do we need to finish? Actually, in 8 minutes. Okay. Yeah. So just by this property of expander that we learned, we have some simple application already. Okay, so let's say that you have a graph G, and suppose you want to know to check connectivity, you want to kind of query if S and T, which is two vertices in the graph, are connected or not. Normally, what you can do is that you can just pre-process a graph in linear time, compute all of the connected component in the graph, right? Maybe do depth first search or breadth first search, whatever. In linear time, you can compute all the connected component. Now, given any query ST, just need to check, right, if they are in the same connected component or not. Let's take just constant time. So that's good. But what if there are failure in the graph? Imagine a computer network or road network, right? You have a graph, and let's say there are some earthquake, and some edge in the graph fail. You have a graph, and some edges fail. You delete them. But now I still want to know if S is still connected to T. Let's say there are just few number of edge failure. But do I need to recompute everything from scratch, right? So we don't want that. If there are small change in the graph, we shouldn't spend total read the whole graph again and spend linear time. So that's wasteful. So this is kind of capture what we want to be dynamic, to be robust. Okay, and it turns out that if the graph is an expander, it's a phi expander. If we know this, okay, actually without any pre-processing on the graph. And given any edge failure D that you want to delete from a graph, we can actually check if S and T are connected in the graph after this failure. Okay. In time, which is just D over phi. So you don't need to read the whole graph at all. You don't need pre-processing. Just need some small time to check this. Okay. By the way, just to make it clear, if D is empty, if you don't delete anything, why does it just take constant time here? No pre-process. Yeah, because expander is connected, right? So there is just one connected component. If there are no deletion, you know that everything is connected to each other. Don't need to do anything. But here, yeah, even if there are some failure, you still need some very small time. So we will continue this next time. Okay, so any question before we stop? All right, thanks. Yeah. Hey. How are you?
Very good. Just kind of learn more about graph theory before.
Cool, cool.
Probably had some trouble earlier this year.
Okay, yeah.
Hi, Professor Sir.
Hey.
Yeah, just want to say hi.
Oh, yeah. Nice to meet you in person.
Yeah, it's a long journey.
Yeah.
I applied to Paris and then.
Okay, good. Let's meet at some point.
Yeah. The thing is, I haven't finished it right now.
Don't worry.
I kind of some problems with the definitions. I think it's harder than I expected.
Okay.
It's like I don't know how to make the things clear. I know how it works, but
So let's email me and we chat more about this project.
okay. Yeah. And a quick question, like when we try to run the maturity the algorithm or the curve graph, it's better to use the representation graph or the line graph.
I'm not sure. Let's check about this later. I'm not sure if or if let me talk to them and we can talk. No,
Okay,
actually.
sure. Hi, sir. My name is Tony. Very nice to meet you,
Nice to
sir.
meet you. Yes.
Yes, sir. Sir, first question, real quick, is I'm an undergrad, and I'm kind of like taking upper level EX classes. I just want to confirm this class is also counted as
Upper
level
yeah.
EX classes.
Yes.
It's not an elective, right?
No, it's
Okay.
ULCS thing.
Got
yeah.
you. Okay. And sir, another thing was like I took 465 Math 465, which is a combinatorial and a graph theory introduction class.
Okay.
And also over the summer, I was doing a direct-to-reading program with a math professor on modern graph theory by Boladas or something,
Okay.
if that went well with the textbook. So I was wondering, are this preparation supposed to be enough for our class? And by the way, also taking 376 over the spring semester as well.
I think it should be enough, except that if you have learned about linear programming.
Oh yes, I also taken the linear programming 510.
Okay, then I
510.
think you should be good. You should be fine. Yeah.
I feel a little bit shaky about linear programming stuff, so I was wondering what are the topics I probably want to do some review, like
So
simplex
just-
algorithm or.
I don't know linear programming algorithm per se. It's just given a linear program, how to derive a dual.
Oh, duality
Yeah,
theorem stuff.
yeah.
Okay.
Like we do already and strong duality.
Okay.
Yeah.
Okay.
Yeah, that
I
should be
see.
enough. Yeah.
Got you. Okay, thank you so much.
Sure.
And I will talk with you on the office hours since there are people waiting.
Sure.
Have a good one.
Yeah.
Just a very short question. I think you lost it at a certain point. What means fee again?
What is what?
What is fee again?
Fee?
Yeah.
Fee is the conductance.
Right.
And which is defined to be like a conductance of a cut is number of edges you need to cut.
Yeah.
And it's a ratio of edges you need to cut and the volume that you disconnect from the ground.
Okay, right. Thank you.
Sure. Yes.
Hi, Professor.
Hey.
I just I'm in the wait list at this course.
You are in the wait list? Okay.
Yeah, and I asked for, I'm in the fourth position of the wait list, and could I possibility join it later?
How do we, actually I didn't know that there is anyone in the wait list. So, and why there is a problem, like people, so what do you want again, sorry?
I just want to ask, is it possible that I join this course?
Should be, I think. So, I think so. Let me just check. I don't think that should be a problem. So,
Okay.
yeah.
And the second question is, which level is this course?
It's kind of advanced, I think. So, like, if you have taken like 477 before, that should be fine. If not, then maybe you need to catch up on some background knowledge a bit. But yeah, so like, what is your background then, by the way?
I just a transfer student from SJTU, and I have taken 376 before,
Okay.
but I have not taken 477.
I see.
I have taken the course like linear algebra and the just this basic course.
Okay, so yeah, in the class, I will soon like talk about linear program. So like you may try to just like catch up on your own then, but it will require you to know about like linear programming in this loop already.
Yeah.
So that kind of thing.
Because I'm doing some research like about the graph algorithms. I'm just like interested in this topic.
I see. Yeah, but okay, maybe if you feel interested, just come and learn about it. And if you feel that after a while cannot catch up or anything, then I would like offer this course again like in a year or something anyway. So, but otherwise, you're welcome to come and learn. Yeah.
Yeah, thanks.
Yeah. Sure.
Because I'm in the senior year.
I see. Oh, I see. There's no I
No
see.
next year.
Okay, no next year. Then just try. Yeah. Let's just.
Do you think it would be really difficult to catch up?
It will take some effort. It will. Yeah. So.
And are there any materials that would recommend it?
I will usually put like a bunch of material linked into the class, but there is no book. Yeah, there's no book for this. Yeah.
And I noticed that no Canvas page for this course.
There is.
Okay.
I just put it up today, so you just need to check. Yeah. Sorry, it's a bit late. Yeah. Okay.
Thanks.
Sure.
Hey, Professor, I had a question about like the research project. So, what do we like? So, how does that work? When are we going to be starting those, or is that like through the semester?
Yeah, it will be kind of throughout the semester.
Gotcha.
So once, like after a few class, I will start like telling you about some open problem